Hello and welcome. The topic of this video is curve sketching techniques. Um, the goal is to accurately determine the important points and asymptote lines of a rational function using calculus, and then to graph the curve accurately by hand. So the main focus would be sketching graphs of rational functions. And so here is the graphing strategy. The first thing we need to do is analyze the function f of x. So this strategy actually works for any given function. So for the first thing we need to do is analyze the function f of x. We want to find that means that we want to find the domain of f. We want to find the x and y intercepts of f if there are any. We want to find the vertical asymptotes and the horizontal asymptotes if any. And we also want to know where f is increasing. F is positive and negative. And then we want to analyze the derivative of f. Mainly, we want to know where the derivative is positive and negative, because that's going to tell us where the function is increasing or decreasing. And then based on that, we also will know where f has local max and or min. The third thing we need to do, so when we are doing when we are trying to find where f is increasing and decreasing, that is where the derivative is positive or negative. Obviously, we need to find the critical points of f. Those are the partition numbers for f prime, meaning these are the points where f prime is 0 or doesn't exist. Of course, then you determine where f is increasing and decreasing, and then that tells you where the local extrema of f occur. And number 3, we analyze f double prime, and which we do to figure out the concavity of the function. So here we need to find the partition numbers for f double prime, which means these are the points where f double prime either is equal to 0 or is not defined. And then we want to find where f double prime is positive or negative, and based on that we can come up with where f is concave up or concave down. And then once we know where f is concave up or down, then we can figure out where the inflection points are, which are the points where concavity changes. And the last thing to do is to plot the x-intercepts, the local extrema, and the inflection points, and then sketch the graph by just using the information obtained in part 1, 2, and 3. All right, so let's do an example and kind of see how each of these steps work. So let's say that we want to find the graph of f of x, which is equal to x minus 3 over 1 minus x. Okay, the first thing we need to do is find the domain, and the domain of this function would be all real numbers except for 1. So it is from the domain is from negative infinity to 1, union 1 to infinity. 1 is not included in the domain. What's the x-intercept? Well, x-intercept is are the values of x where the y-coordinate is 0, that is where the value of the function is 0. So if f is 0, then this fraction is 0, and when a fraction is equal to 0, that means that the numerator has to be 0, and we see that the numerator is 0 when x is 3. So 3, 0 is the only x-intercept for this function. The y-intercept is the point where the graph of f crosses the y-axis. So these are the points where x is 0. So if I plug in x to be 0 in the function, then we get that f of 0 is negative 3, which tells me that 0, negative 3, that's an y-intercept. So this is where 3, 0 is the point where the graph crosses the x-axis. 0, negative 3 is the point where the graph crosses the y-axis. Let's see if there are any horizontal asymptotes. So for that, we need to look at the limit of f as x goes to infinity. And because of the numerator and the denominator, these are just powers of x. When x is big, the limit will be determined by the leading terms here. So x over negative x, and that's negative 1. So y is equal to 1. That's a horizontal asymptote. And the vertical asymptotes here would be when the vertical asymptote occurs at values of x where the denominator is vanishing but the numerator isn't. So in this case, the vertical asymptote would be x is equal to 1. And notice that on the right side of 1, so what's the limit of f of x as x goes to 1 from the right? That is when x is bigger than 1. Well, in this case, the limit, so notice that when x goes to 1, the numerator goes to negative 2. And when x goes to 1 from the right, which means that x is bigger than 1, so 1 minus x will go to 0 if x goes to 1, right? But because x is going to 1 from the right, it means x is bigger than 1. So 1 minus x is negative and approaching 0. So that means 1 minus x is approaching 0 from the left. So this is negative here, and this is negative here. So this would mean that the limit is positive infinity. So imagine that the denominator is something like negative 10 to the power negative 80, right? So if that is negative 10 to the power negative, so if I have the denominator negative 10 to the power negative 80, right? This is a very small, this is a number that's very close to 0, and then this is equal to 2 times 10 to the power 80, which is big. So we see that the limit is positive infinity as x goes to 1 from the right, and so x is equal to 1 is a vertical asymptote. Okay, so we got the vertical asymptote here. And then when, by the way, if x goes to 1 from the left, then this limit would be negative infinity. And then if f of x is this, right? So we want to know, we know that f is undefined when x is 1 and f is 0 when x is 3. So the domain of f, remember, is everything but 1, and we are dividing the domain also at 3. So now we want to figure out the sign of f in each of these subintervals here. So on the left of 1, let's say we pick 0, and f of 0 would be negative 3, so f is negative here. Between 1 and 3, let's pick 2, so it'll be positive. So 2 minus 3 over 1 minus 2, so that's going to be 1, so positive. And f of 3 would be, f of 4 would be 4 minus 3 and 1 minus 4, so that's negative. So we find that f is negative on the left of 1, positive between 1 and 3, and after 3 it is negative 1 again. So the graph of f would be below the x-axis on negative infinity to 1 and 3 to infinity, and it'll be above the x-axis when x is between 1 and 3. F also passes through the points 2, 1 and 4 comma negative 1/3. So basically right here you can see that f of 2 is 1, so f passes through the point 2 comma 1. F of 4 is negative 1/3, so f passes through the point 4 comma negative 1/3. So these are some additional points that we can plot. F of x is this again, and we now want to analyze the derivative. So if you take the derivative of f, and if you then simplify the derivative, you would end up with negative 2 over 1 minus x squared. And you take the derivative by using the quotient rule. So I'm not going to show you the steps for that. So this is the derivative. And now we want to find the partition numbers for this, which would be where it is 0 or undefined. Well, it's never 0 because the numerator is negative 2, and it is undefined when x is 1. So so this is the only, so f prime has only one partition number, x equals to 1. F prime, so I should be saying f has no critical numbers in its domain. Remember, 1 is not in the domain of f. So f doesn't have any critical numbers in its domain. So this should be f here. So let's look at the sign graph for f prime. So clearly, I mean, if you think about it, no matter what x I pick, and as long as I don't pick x to be 1, right? If I pick x anything other than 1, the denominator is positive because of the square, and the numerator is always negative. So clearly, we have that f prime is negative everywhere. So it is decreasing up to 1, and it is decreasing after 1. We should not write this from negative infinity to infinity because 1 is not included in the domain. So this should be exactly how we should write that f is decreasing. This is exactly how we should express the set on which f is decreasing. All right, so we now know exactly where f is increasing or decreasing. And we see that there are no local max or local mean values of f, since f is decreasing up to 1 and it is still decreasing after 1. All right, so that's part 2. The next thing we have to do is look at the second derivative. So once again, here's my f, and here's the first derivative. And first derivative can be written as negative 2 times 1 minus x to the negative 2. And then the second derivative would be 4 times 1 minus x to the negative 3. So we can rewrite that as, and then multiply by negative 1 coming from here. So at the end, if I simplify the second derivative, I would be getting negative 4 over 1 minus x cubed. Again, I'm skipping the details on how to simplify the second derivative here. So once I get the second derivative, again, the partition numbers for that would be where it is either 0 or undefined. It is not 0 for any value of x, and it is undefined when x is 1. So now, by looking at this second derivative, notice that when x is bigger than 1, 1 minus x would be negative, and cube of that would be negative. So when x is bigger than 1, I get a negative number in the denominator, and I have negative on the numerator, so I will get a positive. So when x is bigger than 1, f double prime would be positive, and you can check that it will be negative on the other side. So f double prime of 0 is going to be negative 4, so that's negative, and f double prime of 2 would be, f double prime of 2 would be positive 4, so it's positive. So we see that f double prime is negative on the left of 1, positive on the right of 1. It's concave up from it's concave down from negative infinity to 1, and concave up from 1 to infinity. And we see that f of 1 is undefined. So therefore, we shouldn't be calling, even though it looks like from this that the concavity changing at 1, but this is not an inflection point because remember f is undefined at 1. So we don't have any inflection point. Okay, so number 4 is where we start drawing. So we need to draw the first thing we need to draw are the asymptotes. So x is equal to 1 is the vertical asymptote, y is equal to negative 1 is the horizontal asymptote, and then we have to plot the intercepts. So the x-intercepts, the y-intercepts, and the point 2, 1. So we have drawn this is the y-intercept that we obtained in the first step. This is the x-intercept that we obtained in the first step. These are the green dotted line is the horizontal asymptote, and the blue dotted line is the vertical asymptote. Now let's so 2, 1 is just one of the points that I obtained here that we are sketching. So 2, 1 is something that this is an additional point that we are sketching here. Okay, so we plotted this. Now we need to draw the curve. So how are we drawing the curve? So we know that the function is decreasing from -infinity to x equals to 1. So it is decreasing, and we also know it's concave down. So it's concave down, decreasing, and this is the point it passes through. And it has a vertical asymptote here, so that means it's decreasing and getting closer and closer to this vertical line. And it is always decreasing, but it has a horizontal asymptote at -1, which means that as x goes to -infinity, the graph is getting closer and closer to the horizontal asymptote right here. So this is what we get. And after 1, we know that the function is still increasing, but it is concave up. So it is decreasing, concave up. Here is the x-intercept, here is the additional point, and it has a horizontal asymptote at y is equal to -1. So even though it's decreasing, so it is always decreasing, and as x goes to infinity, the graph gets closer and closer to y is equal to -1, and it increases as x gets closer and closer to 1 from the right. So it goes like this. So this is where we put together all the information that we have obtained from the previous 3 steps. So again, f is decreasing and is concave down here. F is decreasing but concave up here. So this is it. That's the graph. Okay, I'm going to stop the video here, and we will continue with more sketching examples in the next few videos.